The National Electrical Code Section 210.20a addresses the maximum size of conductors and overcurrent protective devices, or OCPs, used in electrical circuits. It states that the ampacity of the branch circuit conductors shall not be less than the maximum load current of the connected load. This means that the maximum size of conductors and OCPs is primarily determined by the maximum load current that the circuit is expected to carry. Considering a scenario where the continuous load is 70 amps, according to section 210.19, the ampacity of the conductors must be sized to at least 125% of the continuous load. This calculation is 70 amps multiplied by 1.25, which equals 87.5 amps. Similarly, according to section 210.20, the overcurrent protection should not be less than 125% of the continuous load, which also results in 87.5 amps. Therefore, in this example, the conductor and OCP should both be rated for at least 87.5 amps. The code requires that the maximum size of conductors and OCPs be based on the maximum load current of the connected load. While factors such as cost, available lug sizes, and specific load requirements do play a role in the selection process, they do not override the fundamental requirement of meeting or exceeding the minimum ampacity dictated by the code. Considering the example, the conductors should have an ampacity of at least 87.5 amps, which is 125% of the continuous load. The OCT, such as a circuit breaker or fuse, should also be rated at 87.5 amps. Several factors influence the selection of the appropriate conductor size and OCT rating beyond the calculated minimum. These include voltage drop, ambient temperature, conductor dating due to bundling, and the interrupting rating of the OCT. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Therefore, conductors may need to be upsized to minimize voltage drop, especially in long runs. Ambient temperature refers to the temperature of the surrounding environment in which the conductors are installed. Higher ambient temperatures can reduce the ampacity of conductors, requiring them to be upsized to compensate. Conductor dating is the reduction in ampacity that occurs when multiple current-carrying conductors are bundled together in a raceway or cable. The heat generated by the conductors can raise the temperature inside the raceway, reducing their ability to dissipate heat. Therefore, conductors may need to be upsized to account for dating factors. The interrupting rating of an OCT is the maximum fault current that it can safely interrupt without being damaged. OCTs must have an interrupting rating sufficient to handle the available fault current at their point of installation. The available fault current is the amount of current that would flow in a short circuit or ground fault condition. Electrical inspectors typically verify this requirement during inspections. Other considerations affecting conductor and OCT selection include the type of load being served, the presence of harmonics, and any specific requirements of the equipment being connected. Different types of loads, such as motors, lighting, and heating equipment, have different current characteristics that may require special considerations. Harmonics are distorted waveforms that can increase the current flowing through conductors and OCTs. In systems with significant harmonic distortion, conductors and OCTs may need to be upsized to accommodate the additional current. Equipment manufacturers often specify minimum conductor sizes and OCT ratings for their products. These requirements must be followed to ensure safe and reliable operation. To summarize, the process of selecting the appropriate conductor size and OCT rating involves several steps. Firstly, determine the maximum load current that the circuit is expected to carry. Secondly, calculate the minimum ampacity of the conductors based on the continuous and non-continuous loads. Thirdly, select a conductor size that meets or exceeds the minimum ampacity, taking into account voltage drop, ambient temperature, and conductor dating. Fourthly, choose an OCT with an appropriate interrupting rating and time current characteristics to protect the conductors and equipment. Fifthly, verify that the selected conductor size and OCT rating comply with all applicable codes, standards, and equipment manufacturer requirements. The National Electrical Code provides detailed requirements for conductor ampacity in tables such as 310.15b16 and 310.16. These tables list the allowable ampacities of different types of conductors based on their insulation type, size, and installation conditions. The code also provides adjustment factors for ambient temperature and the number of current carrying conductors in a raceway or cable. These adjustment factors must be applied to the ampacity values in the tables to determine the adjusted ampacity of the conductors. The adjusted ampacity must be greater than or equal to the calculated load current. For example, if a circuit has a continuous load of 50 amps and a non-continuous load of 20 amps, the minimum ampacity of the conductors would be 50 amps times 1.25 plus 20 amps, which equals 82.5 amps. If the conductors are installed in an ambient temperature of 40 degrees Celsius and there are 4 current-carrying conductors in the raceway, the ampacity of the conductors would need to be adjusted using the appropriate correction and adjustment factors. The correction factors are found in Table 310.15b2. The adjustment factors are found in Table 310.15b3. Suppose the conductor is type THHN copper with an initial ampacity of 95 amps. Looking at the correction factors for an ambient temperature of 40 degrees Celsius, a factor of 0.88 is needed. Looking at the adjustment factors for 4 current-carrying conductors, a factor of 0.8 is needed. This means the adjusted ampacity would be 95 times 0.88 times 0.8, which equals 66.88 amps. Since this is less than the required 82.5 amps, a larger conductor would be needed. In addition to the National Electrical Code, other codes and standards may also apply to the selection of conductors and octs. These may include local building codes, state electrical codes, and industry standards such as those published by the National Electrical Manufacturers Association or NEMA and Underwriters Laboratories OUL. It is important to consult all applicable codes and standards to ensure compliance. The National Electrical Code also specifies requirements for the protection of conductors against overcurrent. Section 240.4 provides general requirements for overcurrent protection, while other sections provide specific requirements for different types of circuits and equipment. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overheating and damage due to excessive current. Circuit breakers are thermomagnetic devices that trip and open the circuit when the current exceeds a certain level. Fuses are one-time devices that melt and open the circuit when the current exceeds a certain level. The type of overcurrent protection device used depends on the application and the type of circuit being protected. The overcurrent protection device must have an interrupting rating sufficient to handle the available fault current at its point of installation. The available fault current is the amount of current that would flow in a short circuit or ground fault condition. The overcurrent protection device must also have appropriate time current characteristics to protect the conductors and equipment from damage. Time current characteristics describe the relationship between the amount of current flowing through the device and the time it takes for the device to trip. Different types of overcurrent protection devices have different time current characteristics. For example, inverse time circuit breakers trip faster as the current increases, while instantaneous trip circuit breakers trip almost immediately when the current exceeds a certain level. When selecting an overcurrent protection device, it is important to consider the type of load being served, the characteristics of the circuit, and the applicable codes and standards. In addition to protecting conductors from overcurrent protection devices also protect equipment from damage. Overcurrent protection devices are often required for motors, transformers, and other types of equipment. The overcurrent protection device must be sized and selected to protect the equipment from overheating and damage due to excessive current. The National Electrical Code provides specific requirements for the overcurrent protection of different types of equipment. These requirements vary depending on the type of equipment, its size, and its operating characteristics. When installing conductors and overcurrent protection devices, it is important to follow all applicable codes and standards. Proper installation is essential to ensure the safe and reliable operation of the electrical system. Conductors must be properly supported and protected from physical damage. Overcurrent protection devices must be installed in readily accessible locations and must be properly labeled. Electrical work should only be performed by qualified and licensed electricians. Unqualified individuals should not attempt to perform electrical work. Electrical work can be dangerous, and it is important to take all necessary safety precautions. Always turn off the power before working on electrical circuits. Wear appropriate personal protective equipment, such as safety glasses and gloves. Use properly insulated tools. If you are not comfortable performing electrical work, hire a qualified electrician. In summary, the maximum size of conductors and opts is governed by NEC 210.20 which states that the ampacity of branch circuit conductors shall not be less than the maximum load current of the connected load. The selection of conductors and opts involves considering factors such as continuous load, non-continuous load, voltage drop, ambient temperature, conductor dating, and the interrupting rating of the opt. Compliance with the National Electrical Code and other applicable codes and standards is essential for ensuring the safe and reliable operation of electrical systems. It is also important to consider the cost of conductors and opts when making selections. Larger conductors and higher-rated opts are generally more expensive. However, it is important to balance costs with safety and performance. It is generally better to err on the side of caution and select a conductor size and opt rating that is slightly larger than necessary. This can help to ensure that the electrical system will operate safely and reliably for many years to come. Ultimately, a qualified electrician should always be consulted to ensure that electrical work is performed safely and in compliance with all applicable codes and regulations. They can provide guidance on the selection of conductors and opts, as well as other aspects of electrical system design and installation.